from B cross V dot V. Sometimes these functions are denoted by just dots. Dot for associative case, Leibniz case, Lie case, they denote as such kind of bracket. In the Leibniz case, we also start to use this bracket. Then today you have seen in physics they use such kind notations for this function. So depending on properties of this F, we will call algebra. This is bilinear, binary operation on B. Depending on properties of this F, you can specify different kinds of classes of algebra. See, if it is associative, associativity means for any three x, y, z, from here you have f of x, y, z is f of x, f of y, z. This is associativity in terms of function f. If you write in terms of the dot, then you will get x, y times z equals x times y, z. This is an associativity condition. The same for Lie, Leibniz, or other classes of algebras. Actually, you may have not one operation. You may have several operations for on vector space, several multiplication. But that multiplication must have some agreement between them, must be set up, because if you take each of them separately, it is not much interesting, because it will be some direct sum. Okay, so talk related to extensions of algebra, not algebras and the applications, too big areas, so only extensions. So I will maybe mention three classes of algebras. One class, first class is Lie algebras, which are very important. Which class has very important application in physics. Another class is Leibniz algebras, which is a generalization of Lie algebras. Then more general, related to these two classes, is called algebras with two binary operations. It's called D-algebras, or if you have associativity of both operations and some condition between these two associative operations, then it is called diassociative algebras, associative D-algebras. So I mostly will talk on third class, since the first class extensions in the properties are given in literature, a lot of information. For second class also, some studies are started. That diassociative case is a less studied case. Just I want to open discussion on diassociative case, just imitating those results from first two cases. And let me start now. Talk extensions of Lie algebras first, then usable. So central extension of associative algebras, then central extension closely related to cocycles. So cocycles on the associative algebras, central extension in cocycles, how central extension can be generated by cocycles. Then application. What does it mean, extension? Extension means you have algebra. See, let me focus on finite dimensional algebra. If your vector space is finite dimensional vector space, then algebra is called finite dimensional algebra. The dimension of algebra is the dimension of underlying vector space. This is algebra E. If you extend dimension, then you will get extension. But you cannot take any extension. So that extension which you want to get must preserve some properties of operation, properties of algebra which has a lower dimension than that extension. So that kind of extension can be given by central extension of algebras. So that's why few types of extensions we have. Maybe I will start to call them first. So this is a simple example. When you have two Lie algebras, M and K, then of course you can introduce in this Cartesian product vector space structure. Addition operation is given such a way, component-wise way, and the multiplication also is given by this way. Then bracket operation is given by using bracket of Lie algebra M, Lie algebra K. So M prime, K prime, they are this bracket in M, this bracket, Lie bracket in K. Okay, so if you consider such a function from K to L, then another function from L to M, then you can see image of alpha and the kernel of beta RCC. So the result, you can write your L, this not only linear transformations, they will be Lie algebra homomorphisms of Lie algebras. So result, you will get Lie algebra L, which is written as a direct sum of two another Lie algebras. They are ideal. In this case, extension is called trivial extension. So result of Lie bracket here is given as product. Lie product here, Lie product here, I mentioned. So now, general case, according to this example, general case, if you have now three Lie algebras K, L, and M, and injective Lie algebra homomorphism alpha, and surjective Lie algebra homomorphism beta, then let us assume we have such kind of condition. Oh, here alpha, here beta, alpha and beta, sorry. This, so image of alpha is kernel of beta. Then you have this Lie algebra is called extension of M by Lie algebra K. So this relationship can be written as a K alpha M, L M and alpha. Okay. So here you can see alpha is injective, kernel of beta is an ideal in L. Then of course you will consider such a quotient algebra which is isomorphic to M because your beta is surjective. So this sequence of three Lie algebras with an extension of M by K if and only if this sequence is exact. This sequence is exact. Okay. So extension is called trivial if you can decompose algebra L into these two ideals, kernel of beta plus another ideal I. It's called split if I or S, sorry, S here not necessary to be ideal. So you have such a direct sum as a vector space. One of them is a kernel, definitely is ideal. Another one is subalgebra. And the direct sum is direct sum of vector spaces. So L is written as a kernel of beta plus S. This is a subalgebra. In that case, extension is called a split. So extension is called central if kernel in the center of L. This triple if kernel of beta is in the center of L, then this extension is called central extension. Now in this case, of course, you will have similar, under extension you will have similar algebra as before. Okay, so one type of extension. This is an example of extension by a derivation of n. Algebra itself has dimension n. Its extension will have dimension n plus 1. So that's why you will extend by 2, 1. The dimension you will increase. So such kind of extension is given by such a derivation delta. So you will consider this direct sum of vector space. This is vector space, this is one-dimensional vector space. Then on this vector space you will introduce such a bracket. X plus lambda delta, y plus mu delta is xyl plus lambda delta y minus mu delta x. So this is a Lie algebra bracket. This is just the value of your derivation times lambda mu times the value of the derivation of point x. So this part is the element of L. So that's why L is ideal in this extension. Now this extension is denoted by L delta. So L delta dimension is dimension L plus 1. So you can, in such a way, you can increase dimension of your algebra. So it is some extension. Okay? So you can, here also you can define alpha and beta accordingly. Similar to that previous example. So this extension is L delta is called extension by derivation. Why extension by derivation is important? Because let me show this slide. So we have these 3 or 4 types algebras. No, this one is just a few classes. A lot of other classes of algebras which are important in quantum physics. It's just loop algebras, Cauchy-Modi, then beta algebras, then vector algebras. Why I brought this, bring these examples, names, because they are closely related to extensions. See, Cauchy-Modi algebra is extension of loop algebras. Beta algebras extension is the rational algebras. It is proven. Okay, so what's the loop algebra? Loop algebra is defined as follows. If you consider Lie algebra L, then you will consider such kind of elements and their combinations, a linear combination of such kind of elements. Then on that span of these vectors, on that span of these vectors, you can define such a bracket lambda to the power mx, lambda to the power my is lambda m plus n bracket on L. Easy to verify. This is a Lie algebra bracket. Resulting algebra now infinite dimensional algebra. Even your algebra is finite dimensional because of this lambda to the power mx. Linear combinations may be infinitely many, but they are linearly independent. So that's why result you will get the infinite dimensional Lie algebra. So this Lie algebra is called loop Lie algebra. This is closely related to loop groups. So if we come to these classes of algebras, then of course with algebra is Lie algebra vector fields on unit cycle. Whereas algebra is used to establish class on fragment. Okay, now application of extensions related to these 4 classes I will talk later. Then let me now to start to talk on associative dialgebra. So you have 2 functions now. G from B to BG, but these 2 your operations. By the way, in these slides, one of them is denoted like this, and another one is denoted like this. It's called left product and right product. Why these algebras are important? Again, because there is a close relationship between associative algebras and Lie algebras. You have Lie and associative algebras. Then there is a generalization of Lie. It's called Leibniz. That identity for Leibniz is written as follows. So x times y times z equals x times z times y plus x times zy or y. This is called Leibniz identity. Leibniz identity. It is generalization of Jacob identity. Why, if you assume that xy is minus yx, then Leibniz identity reduced to the Jacob identity. So that's why, under this condition, any Leibniz algebra is a Lie. And this is more general identity. So that's why the generalization of Lie. Now, of course, Loder in 1990s tried to find counterpart of associative algebra, because if you have associative algebra, there is a functor from category of associative algebras to category of Lie algebras, which is given by xy minus yx, passing from associative algebras to Lie. Then, can you find some object here which plays the same role as associative algebras for Leibniz algebras? He found it. This passage can be given so you can see here two operations. So that's why dissociative algebra. So the result is he created so-called category of dissociative algebra. Then, of course, it is very interesting to study this class of algebras. So if these two operations coincide, then any associative algebra is any dissociative algebra is associative algebra. Associative algebras are particularly for dissociative algebras because it is assumed these two operations are associative. Then plus some identities must be satisfied. So here is definition of associative algebra, associative dialgebra. Associative dialgebra is vector space with two this kind associative operations. Associativity is given. See? Then these two operations are related by these three axioms. So altogether you will have 5 axioms. 2 associative algebra axioms plus these 3 axioms which are related to 2 operations. Okay, then of course you can define homomorphism. Homomorphism from one direction to another dissociative algebra. It is a linear map satisfying this condition. Of course, you should keep direction of operations. If you change, of course, you will get not a proper homomorphism. It will be something else, but still can be studied. So it is defined this way, only this way is a homomorphism. Okay, the canal image can be defined naturally. Any bijective homomorphism is called isomorphism. If you have one algebra homomorphism from the same algebra to itself, it is called endomorphism as usual. If it is a bijection, then it is called automorphism. Okay? Then it is a definition of the center. The center of P is defined by this way. It should be those elements of P which kill all elements of all other elements with respect to both operations. This is the center. So, in algebraic point of view, we are interested in classification problem. What you will do? What can we classify? If you classify algebras in dimension C2, then to classify in dimension 3, you should produce first algebras in dimension 3. But that extension to dimension 1 or 2 and 3 can be given by that I already have mentioned, by using central extension or by using derivation extension. Okay, so but here before what the researchers have given classification, they just took so-called structural constant, fixed basis, take structural constants, and then putting that structural constants to identities and solving some system of equations, find the list of algebra, then among them you should find which algebras are isomorph to each other. That process is very difficult. Sometimes we can use computer programs, sometimes by hand, but still it's not easy to do it. So that's why you should search some, create some other, some methods to create algebras of high dimension. So extension is one of the approach, extension, central extension approach. One is such kind of approach. Okay? I gave here some references which where that naive method has been used. Here, which method which I will use is action of automorphism group in the lower dimension algebra on second cohomology group. So that is given by graph in Lie case and the associative case. Then for Leibniz case, we apply my student this method also. For Leibniz case also, here I will give for diassociative Leibniz case. Okay? Alright, so regarding that four classes algebras, Class-Moody algebras are can be obtained by taking loop algebra of classical simple algebra. First you make consider loop algebra, corresponding loop algebra, then extended by derivation. By Class-Moody algebra can be obtained by these two extensions. You should first to consider loop algebra corresponding to generated by simple Lie algebra. Then to that you should apply extension by derivation. In that case you will get Class-Moody algebras. Then Virasoro algebra is extension of weak algebra, which is already I have mentioned. I will skip this part. Then let me now no more on Leibniz on Lie algebras. I will talk now on associative dialgebras. Okay, so we have now three algebras, three diassociative algebras, D1, D2, D3. Then D2 is called the extension of D3 by D1 if there are associative dialgebra homomorphism alpha and beta, which this sequence is exact. If such can homomorphism exist, then we call D2 extension of D3 by using again, it is called trivial if you have direct sum of algebras. D2 can be written as a general and it's ideal. Of course, in this extension, central extension, you may have two central extensions which define the same two types. Algebras can be defined by one central extension. That central extensions are called equivalent central extension. Means one central extension and a central extension. They are called equivalent if this condition holds. This is extension. This central extension means center of D2 must contain kernel of beta, or must be D2. So. Okay, so central extensions are closely related to second cohomology group. Let me now start to define cohomology group of diassociative algebra, second cohomology group, by using some cosine boundaries. Okay, now let us consider diassociative algebra. Then, because of diassociative algebra has two operations, two binary operations, of course, you should have two functions, q theta 1, theta 2. So here theta comes as a component theta 1, theta 2. Bilinear maps T1, theta 1, theta 2 is called cocycle if it satisfies these conditions. Actually here 5 conditions according to axioms of diassociative algebra. These conditions we can generate from the associated algebra axioms. Because why these functions are given this way, you can understand after this theorem. Yeah. So you have the associative algebra. Then you have these two functions. If you consider this, then if you define operations this way, then d theta is associated with the algebra if and only if theta is a 2 cocycle. So 2 cocycle means they satisfy these conditions. So that's why between extension, central extension, d theta, and for theta to be cocycle, we have such a condition. So this is a central extension. Then this is diacetyl to be for this extension to be diacetyl algebra. This must be cocycle. Okay. So there is a co-boundary. Let me just collect all cocycles in Z2. Then addition operation we can define this way. Multiplication by scalar also you can define this way. Result set of all cocycles is the linear space. Then there is a special 2 cocycles which is given by the following lemma. If you consider any linear map, then you can define phi 1 and phi 2 as follows. Phi 1 xy is new first operation y, and phi 2 is new second operation y. So you have two such kind, phi 1 and phi 2. They satisfy these conditions, these all conditions. So that's why they are cocycles, 2 cocycles also. So phi is cocycles. But these cocycles defined by such kind of linear maps are called coboundaries. Now you have cocycles and coboundaries. Set of coboundaries we denote by B2 dV. Then this is a subgroup of Z square dV. Then of course if you consider cocycles in the factor group with respect to coboundaries, this group is called second cohomology group of diacetyl algebra D with values in vector space trivial module D. So 2 cocycles, theta 1, theta 2, if different is coboundary, then they are called cohomology cocycles. So here, each of elements of each H2, they are non-cohomologous to each other cocycles. Okay, then already I mentioned regarding this theorem. Some proofs I have here. If time allow me to do it, maybe I will focus some of them. Otherwise, I will just proceed. So here is lemma. If you have 2 cocycles theta and phi, then diacetyl algebra generated by this cocycle and the diacetyl algebra generated by this cocycle plus this coboundary are the same. So that's why isomorphism of diacetyl algebra generated by cocycles, they are up to coboundaries. So you can ignore coboundaries. You can take cocycles and then construct the extension. This is a central extension. Here is a proof of this theorem. this isomorphism given by this rule. D theta plus phi is x plus nu x plus nu x plus d. You can easily check this is this gives this one. Okay. Right. So this is for one operation is given here. The fact that it is a two-step operation. This left operation, right operation case can be proved similarly. So any cohomologous two cycles define the same algebras. So that's why you can ignore. Now there is such kind of identification. If you have G squared dV, you can identify it by G squared df k, replacing cocycle by k cocycles. How can we do it? Because if you take cocycle, then cocycle has two components, one theta 1 and another theta 2. Now, if you take this one and expand it with respect to basis of b, then you will get such kind of linear combination with coefficients theta. If you denote the components as a theta 1i, here theta 2i, then you will get another two functions. But this function's value now in f. And previous function, this function's values are in v, but after this expansion, you will get the functions here whose values are in f. So that's why you can replace theta by these components. So you have theta, k components for first part, and the k components for second part. Now, here is lemma related to cocycle and its components. Theta is cocycle if and only if its components are cocycles. You see here, theta 1, theta 2, z2 dv. But here, theta 1i and the theta 2i, for each of them we have components. So this is cocycle if and only if they are cocycles. Here cocycles with value in v, here cocycles with value in f. So you can get such an identification. The same for coboundaries. So now, just ignoring cocycles with value of f of v, we can start to deal with cocycles with values of f. The coboundaries also the same. So result, you will get such a central extension. Central for each element of v squared dv, you can construct such an algebra d theta. D theta, it is extension of d, because dimension of course will be more. Because of if this is not trivial, of course. If it is not trivial, of course it is alpha is monomorphism, so that's why there is a part coming from v. This is just factor. So that's why dimension of d much less than dimension of d theta. So this is an extension. This way you can get the algebra of higher dimension. Here is the proof of that result. This one is classical. There exists one-to-one correspondence between elements of h squared dv and the non-equivalent central extension of the S to algebra D by trivial module B, because here the product is trivial, zero product in the vector space. Okay? Here is a proof of this result. What we will do, this proof. We'll first to construct by taking cocycle, we will construct d theta, central extension of d. Then if central extension is given, then we construct element of h squared db. So here is given one part, construction of the cocycles. Here is cocycle theta, which is constructed by such kind of function. Function is given this way, which is a section of S, beta and S. So result, you will get B1, B2, which is defined as this way. And if you combine now beta and Bi, then you will get cocycle. Because alpha is injection and alpha is the monomorphic, so you can consider alpha minus 1. So theta I is alpha minus 1 composition of Bi. It is required cocycle. Okay, now, of course, now what we'll do, I will consider now action of automorphism group of D. D is, say, diassociative algebra of low dimension, Then I will calculate the automorphism group of D. I will calculate second cohomology group of D. Then by using this automorphism group of D and this cohomology group, elements of cohomology group, I will construct d theta extension of D. How to do it? So it is given as follows. Let me show first the algorithm. If I consider diassociative dialgebra D prime, if its center is not trivial, then I will take that center as a V. In center, all products will be 0. So that's why I can take V as center of that algebra. Then, of course, I can consider D, which is D prime over Z D prime. This algebra will have dimension much less than original algebra D prime. So now, if I take cocycle theta from h squared db, I can find such a cocycle that D prime can be written as, can be generated by as a central extension of D by using this cocycle. That is the point, because this algebra dimension is higher than dimension of algebra D, but it can be represented as a central extension of D by using element of H2 dB. You see, you can see here, this group cohomology for D, not for D prime. So that's why you will take element of cohomology group of D, which is values in D. Then, by using this cohomology cycle, you will construct D theta. So that D theta will be your D prime. Here is given explicitly how to use it. So D, the associative algebra of dimension n minus s. Then you will consider S dimensional V as dimensional center. Then D prime over D, Z D prime is D. So to construct this D prime, what I will do? I will take cocycle in the co-boundaries. I will find this with values in F, with values in M, or in the dimension. So I will take construct cohomology group of D with values in F, then start to act by this automorphism group to this cohomology group and define some subspace having the same dimension. So finding PH, then of course it will be a lot of such kind of algebras. Then I will start to verify which of them are isomorphic. Okay, so here is given which kind of algebras I should identify, which is given by this theorem. Okay, if you have two cocycles, one is theta, another one omega. These two cocycles define the same algebra, so isomorphic algebra, if and only if there exists element of automorphism group of T such that acting two components of omega, I will have some subspace of second cohomology group, and I will construct components, subspace of components of theta. You see here phi of omega ji, which is components of this, and this is components of theta. If they span the same subspace of H2df, then these two algebras are the same. So that is the point. What will do? I will take such kind of two cocycles, then start to verify for these two subspace will be the same. If they are the same, they are isomorphic. So that's why I will identify such kind of algebra generated by delta and omega. Here is a proof why we can get such a isomorphism. Here are some references. Okay, so that's it. Any questions?
Questions?
Not so much related to physics, but it's open. You can apply for physics, because there is another class of algebras called the dendriform algebras. They are exactly somehow related to physics, because a lot of papers related to dendriform algebra. You know, so that is more physical approach for dendriform algebra. This is a pure algebraic. But I hope after some time they start to use to apply dissociative algebras and the Leibniz algebras physics after I don't know after 200 years. Because 200 years ago nobody thought the algebras can be applied in physics. Sometimes they are not mathematicians starting us why you are studying algebras which if they don't have applications. So the answer for them is just this thesis. Actually, 200 years ago, you didn't know, nobody knew the Lie algebras can be applied so extensively in physics or other areas of science.
I have a question. So you give many equations, and from some algebra structures, often from the equation from the small dimension. Okay. So whether we also can define the equivalence for the two equations. So whether it is equivalent to the result, the isomorphism of the algebra. Yeah, I mean the equivalence of the equations, whether it's the same as the result of the algebra.
Okay, you take least in dimension, say low dimension.
Okay.
The one of them, say you will take 1D from that list. You already have given a list.
Okay.
Classification, right?
Right.
You will take this.
Yes.
Then taking that cocycle, you will extend it.
Okay.
Extend it. Of course, in extension you may have many.
Right.
So they are according that theorem. According that theorem, what can we do now? We will pass to action of automorphism group on second cohomology group.
Yes.
Then calculate that theorem. Apply that theorem. They are isomorphic and only if in Grassmannian you will have the same subspace or this theorem. You have this cocycle and this cocycle. Of course, they are isomorphic if and only if we have if there exists automorphism of D, which this subspace and generated by this subspace are the same.
But the question is, usually when you study the influence of the cocycle of the cohomology, it's very complicated to give the computation.
Classification problem, not easy. You know it.
Yes,
so that's right.
Problem.
Because
so that's the reason I ask those questions. So usually, of course, the classification we have output from the decision of motivation, but usually it only can partly give some results.
Yeah, because the classification, direct classification is very difficult. There is no standard way to classify. There is no algorithm yet. So that's why we have to use what we have or create something. But still it is not complete. I mean, classification is not a good job. Why? Because you will classify, then after 1 year or 2 years, probably start to criticize me. I missed one algebra, or I got some extra algebra, and so on and so on. Of course, then I classify. I will revise some list again. Somebody else start to be the probe also. You see, such kind of things in the algebras case very often. So that's why I hope maybe somebody start to beat me also. No problem. This is a research. This is our thing to do research.
Oh, another question. So extension will also depend on the field, right?
Yeah.
So given the field, given the result.
Sure. Yes, this is a general way.
Yeah,
in each specific field case, you will, of course, you have to put some conditions, depending on characteristic, maybe, or algebraic closeness or not, or over finite fields or not. Thank you.
The next step, Prof. Isamiddin again.